Welcome to Study Loop.
Hello everyone, today we're doing chapter 17, problem 26. And this problem tells us that early structural studies of benzene had to explain the following experimental evidence. When benzene, so we'll draw benzene, was treated with diatomic bromine and some sort of Lewis acid, such as a single substitution product was formed with a molecular formula of C6H5Br. So a single product was formed that looks something like this. And it says that when this product was treated with another equivalent of diatomic bromine, three different compounds with a molecular formula of C6H4Br were formed. So we take this and we add another equivalent of diatomic products. We have three different products being formed. This is one of them. This is the other one, and then this is the last one. So this is a two-part question. This question asks us, explain why a single Kekuli structure is consistent with the first result, but not with the second result. So what does that mean? So that structure means representing your double bonds or your bonding with single lines. So you don't actually investigate any resonance. And then part B asks, explain why a resonance description of benzene is consistent with results in both reaction. So let's start with problem A. So when we're drawing a Kekuli version of this benzene ring, what that means is that even though we know that these three bonds in benzene ring are actually a hybrid of existing in both this state, it's in a hybrid as with existing in this state. So in essence, what we have is a hybrid system where these double bonds are just flipping between these two states. So we actually get partial double bond characteristics in every single carbon-carbon bond. So in essence, we're not able to isolate one of these forms or the other. We get a benzene ring that is in some sort of hybrid state with double bonds either being localized like this or like this. And that's what gives it the partial double bond characteristic at every single carbon-carbon double bond. So if we were to draw this Kekuli structure, meaning that we draw the actual bonding and not the hybrid form, we will get a monosubstituted halide addition on this benzene ring. And it doesn't matter where you actually draw this bromine ion, it will always fall on a carbon that is doubly bonded to another carbon. Doesn't matter where you draw it, you will always get the same identical product. But now, if you were to draw these structures, it's not consistent with only getting three products. Because you see here, if we can get ortho-meta and para substitution, well, we have two ortho positions, two meta positions, and one para position. Well, we see that in a product, we have one ortho, one meta, and one para product. But these can't actually be this can't be true. Why? Because in essence, if I were to draw benzene with the non-hybrid form, so just imagine benzene only existed in this form that we're drawing here, and we know that the single bromine attached on this carbon here, well, then I could get another ortho product that is not consistent with the three products formed on this carbon. And this would be different than this product. Why? Because these two bromines are attached on carbons that are doubly bonded to each other, while now these two bromines are attached on carbons that are singly bonded to each other. So because these two bromines are bonded to double bonded carbons and these two are bonded to single bonded carbons, these would essentially be different products. So because these would be different products, we would actually get 4 products if we were following the Cooley model of drawing these structures, not the 3 that is identified in the question stem. But now moving on to B, explain why the resonance description of benzene is consistent with these results is because we know that, once again, in part A, in the first reaction, only one product will be formed. Why? Well, because all the carbons are identical. But now if we take this first carbon, this first product, and add diatomic bromine, we would only actually truly see these 3 products, ortho, meta, and para isomers formed, one of each, because this structure here, this ortho substituted structure here, and this one on the bottom are actually identical. 3 arrows meaning they're identical. These are the same structures. Why? Because we know that benzene in resonance structure actually is a hybrid between these 2 forms. So in essence, these 2 structures are actually represented by a benzene ring that has their double bonds all around the ring. And then if we draw 2 bromines on an ortho position or 1 bromine on an ortho position, doesn't matter if you flip it 180 degrees or like this, they represent both of these structures here. So because each of the carbon-carbon bonds are identical and they're in some sort of intermediate length between a single bond and a double bond, we know that every single carbon-carbon bond has some partial double bond characteristics, making them all identical. So we don't actually get 2 separate structures for this ortho substitution. We only get 1. Therefore, resonance explains why we only get these 3 products shown here.